Happy weekend, chemistry folks. Today's chemistry lesson is brought to you by Paula Abdul. Before she was a judge on American Idol, she was a pop star singing songs like Opposites Attract. And I thought that was very apropos for what we're talking about today, polyatomic ions and some more ionic bonds. So let's go ahead and take a look at the starter that we had on Thursday. Many of you were not there because of, I suspect, not feeling too well. And I empathize with that and can give you a little bit of a leg up on this week coming up by doing the starter that we had over. So your starter is going to be to answer these questions. What is a polyatomic ion? Give a few examples. What are the first two steps of drawing polyatomic ions, the Lewis structures? Number 3 asks to complete the first two steps for the Lewis structures, and 4 also asks to complete some steps for chlorate, which is a specific polyatomic ion. So I'm going to give you about a couple seconds to pause the tape now if you want to do these questions, and we're going to go over the answers very shortly. Alright, it looks like you're ready to go over these answers. What is a polyatomic ion? Give a few examples. Polyatomic ion is a group of bonded atoms that collectively carry a charge. So instead of just having one atom with extra electrons or extra positive charges from electrons, they are a group that are covalently bonded, and all together they have extra electrons than they should, or less electrons than they should as a group. Okay. Some examples could be chlorate, oxalate. We have some hydroxide ions that we can put in there as well. What are the first two steps of drawing a polyatomic ion? Well, those you are going to need to memorize, and the first two steps are going to be to find the formula using reference table E in your chemistry reference tables and determine the valence. And last but not least, we need to look at how to do the steps for chlorate. And I'm going to start you off by saying the first step is to find the structure. The structure is going to be, the formula is going to be ClO3 2-. And ClO3 2- is where we're going to go ahead, and that'll be our departure point for how we need to do this. So let's review the 6 steps again for drawing these Lewis structures. Step 1 is to refer to the chemical formula. So chlorate is given on this chemical reference table, called selected polyatomic ions. And it is down here. ClO3- is chlorate. The 3 is a subscript to let us know that there are 3 oxygens in here, 1 chlorine atom in this group, and all together they carry an extra negative charge. So there's 1 extra electron than there needs to be. Let's take that information to the next step. Step 2 asks us to look up each element on the periodic table for valence electrons. And if we look at the periodic table, we have 2 different types. This one is from your chemistry reference tables on the left for oxygen, and on the right is the one in your textbook. Both of them give the same information, that just come from different places. If you look at that second number in that simple electron configuration, 2-6, or here 2-6, that second shell, that last shell, that's our valence shell, and that's how we get our 6 valence for each oxygen atom. We also look at the same information for chlorine. Again, we're looking at that last number, that last shell, and that's how we get that there are 7 valence for each chlorine atom in this. Now that we know that, we can go ahead and start with step 3. We need to add in any negative charges or take away any electrons for positive charges. Once we have done one last thing, though, with this, and that is to multiply if we need to. So you see that 3 there is important. We have 3 oxygen atoms here. We know that each one has 6 valence. Well, 6 times 3 is the total valence for oxygen that we have available. The total valence for oxygen will be 18. For chlorine, it's a little easier because we don't have a subscript here. That lets us know that automatically it's 1. So 7 times 1 is 7 valence total. If you're having a hard time with this part, I advise you to look up on YouTube how to calculate valence electrons. Alright? The ion altogether, you might say, has 25 valence total, but you have to remember this charge here. This extra charge lets us know that we have an extra electron, and there's 1 extra. So now when we add all these numbers up, 18, 7, and 1, we are going to get, pause if you want to stop right here to see if you can figure it out. The answer is 26 valence electrons total. To help us out with counting, instead of counting a bigger number like 26, if we divide by 2, we know how many pairs of electrons that we need. So we have 13 electron pairs total that we need to place. We're going to use this information with our original formula to figure out how the structure should be written. So the very first step is to put the first atom in the center and others around it. So we're going to have our Cl and O, O, and O around. What we'd like to do as well in here is now figure out how we're going to place these electron pairs to satisfy the octet rule. I like to start with the most electronegative element because that's the one that's going to want the electrons the most. So that will, in this case, be chlorine. And to satisfy the octet rule, chlorine is going to need an extra. And so now I have just placed 2, 4, 6, 8 electrons around chlorine. It satisfies the octet rule for chlorine. I have all these oxygens, which are also pretty electronegative, but not as electronegative as chlorine around that. So I'm going to need to put some electrons around those as well. Since I used 1, 2, 3, 4 pairs, I still have 9 to place. So I'm going to start just by placing them equally around the oxygens here. So I have 3 that I've placed there, so I have 6 left to place. I have, once I put all 6 of those pairs down, I'm just going to check really quickly to see if I satisfy the octet rule for everything. This oxygen has 8 electrons available to it. Chlorine, we already said, has 8 electrons available to it. This oxygen has 8 available electrons. This oxygen has 8 available electrons. And just quick count to make sure that we haven't cheated here. We should have had 13 electron pairs. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 that we placed. So we have placed the correct number of electrons and satisfied the octet rule. Step number 6 is going to be to change all these lone pair bars to dots if you use the bars. If you would not like to change these or do this step in its full extent, you can just avoid using bars when you're doing lone pairs and only use bars when you're making these bonds if you'd like to kind of condense these steps a little bit. But if you like the bars, which I kind of do, you can continue to use them, but make sure that in your final answer you get rid of that. Let me show you what that looks like very quickly and easily. We're only going to get rid of the bars that are not bonds and add a bracket there. So I just replaced every lone pair bar with double dots to show that. And the reason that we do that is to make sure that anybody who is checking your chemistry regents will understand your notation, because it's not very common to use the bar. The last thing that we need to do after we've added our brackets to show this is to go ahead and represent the extra charge on this, and now we have the full Lewis structure for chlorate. Okay? Check your answers, pause if you need to, rewind if you need to, see what you need to do. I'm going to pause it here. Alright, we're back, and let's take a look at a couple more examples. One is going to be carbonate. Carbonate, again, is also on this reference table that you need to know. Carbonate is here, and here's our formula. CO3, 2-. The 3 is a subscript, lets us know that there are 3 oxygens. The 2- is a superscript that lets us know that it is a -2 charge. We're going to take this with that same kind of information that we looked at before from the reference table and our periodic tables to find out the valence for oxygen is 6 each. The valence for carbon is going to be, again, the second number, the last number in that simple electron configuration, 4 each. We're going to use this information to multiply by the correct number that we need as well to make sure that we have accounted for all of our charges. So again, there's a subscript of 3 here. That means that there are 3 oxygens. So in this one as well, oxygen total has 6 times 3 valence, and that's 18 valence total. Carbon has 4 times 1 total, since there's no subscript. That's 4 valence total. Don't forget that the ion has an extra 2 negative charges, so that means that we have 2 extra electrons. And when we add all these numbers up, 18, 4, and 2, we get 24 valence electrons total. Let's divide that by 2 to get a smaller, more manageable number of the electron pairs that we need. And that's going to give us 12 electron pairs. Now with this information, 24 valence electrons total, or 12 electron pairs, whichever way you'd like to think about it, we're going to go ahead and continue to put the first atom in the formula in the center and the rest around it. Okay, and I'm going to go ahead by just connecting 3 bonds here so that these atoms are all connected in a way. when you connect these bonds, avoid making triangles, avoid making cycles. There are very few cyclic atoms that we need to worry about in terms of drawing our Lewis structures and polyatomic ions especially. Here, I also want to start with the most electronegative element, which is going to be oxygen in this case, and start filling up the rest of my electron pairs there. So far I have 1, 2, 3, 4, 5, 6 pairs, and I have 6 more to go. I'm going to put them evenly around the rest of the electronegative elements, in this case oxygen. And I need to now make sure that the electron pairs are satisfying the octet rule. As you see here, this oxygen is very happy with 8. This oxygen has access to 8 electrons because each of these bars represent 2. And this one, 2, 4, 6, 8. Very happy. However, the carbon, not so much. Carbon only has access to 6. So what will happen here? Pause if you're not sure to think about this. I'm going to go over the answer in just a second. I really want you to consider what do you think will happen since we cannot add any more electrons to this. We have used up all of our 12 pairs. And here's the answer. The answer is that one of these oxygens with these lone pairs will put that into, I guess you could call it the collective plate between this carbon and oxygen for it to share. Now this lone pair can come from any of these oxygens since this is more or less the same structure no matter how I turn it. But just for the sake of argument, I'm going to say that this lone pair from this oxygen is going to go ahead and satisfy that for both of those atoms. And so this is what happens. Carbon now has 2, 4, 6, 8 available to it, and I did not add any electrons, you notice. This oxygen has 2, 4, 6, 8 available to it. This one still has its 8, and this one still has its 8. Now everybody has satisfied the octet rule, and this is the structure that we see. You also notice that the geometry of this may have changed a little bit. This is more of our trigonoplanar geometry, where there's 180 degrees between each of these. And that is because these charge centers here, this bond around this carbon, want to make as much space as possible between them. That's a little bit of review from a previous unit. So now we just need to finish step 5 and step 6. That's to change any of these lone pair bars to dots and add brackets and charges. So we're going to leave these bonds alone here. We're going to change only the dots. The lone pairs to dots. Add the brackets. And we need to copy this charge right there to make sure that we have written out the Lewis structure correctly. So those are basically a review of what we ended in class on Wednesday. Thursday was what we ended in class with. And the next step is going to be something a little bit new that we've not talked about in class if you missed it. Okay, but if you were in class on Friday, this is a bit of review as well for you. Practice. Look up Lewis structures of polyatomic ions with Mr. B. And the link to look at is this one, www.youtube.com/watch?V equals capital W, capital I, capital A, lowercase j, DONI, 96, capital Y. I'm going to make sure that this link is in the box below as well. So we're almost there. This is the new stuff now that we covered on Friday. The new stuff that we covered on Friday starts us off on page 156. And we're going to take a look at this part up here. It asks you to review the previous pages on writing Lewis structures of ions and ask how can we draw the Lewis structures of this ionic species between magnesium and hydroxide. Okay, it's kind of given to you in this table. I want you to take a look at this table very carefully and think a little bit about what these things are. I'll give you a little bit of a hint. In a minute, we're going to make use of this section here for annotations. And that's where the answer to number 2 is going to come from. But just taking a look at this table here that I've kind of already set up for you, what are some of the similarities and some of the differences between them? Okay, so go ahead and take this moment to write in this section to the left of the table what some of those similarities and differences are. Pause the tape now if you are going to go ahead and do that. All right, and now I am back to business over here. I'm going to give you a couple of the things that I see that is the similar and different between these two ionic species. The first thing that I find that is similar are these things. Okay, Both have 2 anions here. That's the ratio, and 1 cation. The positive charge is one thing. The negative charge is carried by 2 things. So in this one here between magnesium and chlorine, or I should say chloride ion, and this one here between magnesium and the hydroxide ion, you have both of those situations going on. Similar to that, the structure is similar, so that you can see the pattern that this makes looks to be pretty similar. Negative, positive by 2, negative. We can also see some differences though. So outside of that, we have some monatomic ions on this one versus polyatomic ions on the right. And the last thing that I'm going to go ahead and get you started with is when you have more than one polyatomic ion in the formula, there's something here that's added that is not added here. And we're going to be really focusing on that for the rest of this worksheet. All right. And that thing that is very different is you need to use parentheses to show that there are multiple instances of a polyatomic ion. Let me say that again. We use parentheses in the formula when you have more than one of the same polyatomic ion. So, since we have 2 hydroxide ions here, and we know it's polyatomic because it has more than one atom inside the brackets bonded together, and they all carry a charge. Since we have more than one of those, we have to show that with a 2 there. I'm going to show you what will be wrong. You might think that this formula could be written like this. Mg, and since I have 2 oxygens and 2 hydrogens all together, bonded both ionically and covalently to create this thing, you might think MgO2H2 is a good way to write this. This is not a good way to write this because it does not represent really what's going on. And really what's going on is not that all these things are bonded together in some kind of covalent way, but there is 1 Mg and 2 of these groups of OH, 1 Mg and 2 of these groups of OH that are bonded. And so this is what this means. This 2 subscript outside of the parenthesis means that there is a group, a hydroxide group, and there are 2 of them, 2 instances of that group in this ionic species. Okay? List 3 examples of monatomic ions and 3 examples of polyatomic ions. I think you can pretty much do that on your own if you pause the tape in a moment. What is the major difference between writing formulas with monatomic ions and polyatomic ions? My hint to you is look to the left. Remember what we just talked about. Go ahead and pause the tape and fill these 2 out. We're going to move on in just a second. Okay, we're ready to go ahead and move on. This last page is the final thing that we were able to finish in class. With all of the practice that we did with polyatomic ion drawing. And so here is kind of where what we just talked about is going to now coalesce into. We remember the crossover rule, which states that this charge here on the anion, the charge on the cation, they essentially are the basis for figuring out the subscripts. So in other words, based on the crossover rule, since I have a -1 charge on bromide, that means I'm going to have 1 iron 2+ ion. And since I had a +2 charge on this iron ion, that means I'm going to have 2 bromide ions. Okay? This is a review of what we did before. Nothing really fascinating going on here. Let's take a look at how this translates into a chemical formula, or an ionic formula in this case. This iron gets carried over. This bromine gets carried over. This bromide, I should say Br. And then the last thing that we need to do is carry over any subscripts that are not 1. So this one we don't need to carry over because it's 1. This one we do need to carry over because it's 2. And it's going to be written as a subscript for our bromide. Okay, so altogether when we write our ionic formula, it's going to be FeBr2. Take a moment to figure out for yourself, and it's very similar but somehow different. Calcium 2+ and hydroxide anions, how would they form together? Pause right now, and in about 5 seconds I'm going to go over the answer. Alright, we're ready to go over the answer. Calcium 2+ and hydroxide 1-. You're going to have the same exact ratios. We have 1 of the cations and 2 of the anions here. And very similarly, I'm going to go ahead and carry that over. I'm going to carry this over. To get us started, we're going to move this 2 over as a subscript, but this is not quite right just as it is here, because this right in here would tell me that there is 1 calcium atom, 1 oxygen atom, and 2 hydrogen atoms in this formula. And that's not exactly what we're talking about. We want to represent 2 of these groups of hydroxide ions. So in order to carry that idea that this 2 applies to this whole thing, I need to go ahead and add my parentheses. And again, when you use a polyatomic ion that has more than 1 polyatomic ion, the same type of ion, we're going to use parentheses to show that. Okay. Let's take a look at the last 4 examples. The first one in each of these rows are the simple structures with the monatomic ions. Again, with the crossover rule, we get 2 magnesium and 2 oxygen, which we can reduce to 1 magnesium and 1 oxygen, since 2 divides into both of those equally. When we write our formulas, very simply, we're going to carry over the structures for both of those 2 things. And since there is only 1 atom of each type, we don't need to worry about subscripts. And we just write them together. Let's take a look at these here, which looks a little uglier. We have the same exact ratios, 1 copper cation and 1 sulfate anion, SO3 2-, that's our sulfate anion. When we write our formulas, Cu is going to go carry over, sulfate is going to go and carry over. And very similar to what we see above, you might be tempted to go ahead and write your parentheses around that sulfate. You might be tempted to write that. While this is not a whole lot of incorrect information, we don't normally write the parentheses around an ion unless there is more than 1 of that instance. So for example, the sulfate anion here, there's only 1 of them, so there's no need to write a parenthesis, because when we see SO3, we kind of understand just by doing this enough times that we're talking about an ionic species, and we recognize that even in how we name this, which you're going to be looking at a little bit later. So we actually don't need those parentheses there, and we'll just write them together, CuSO3. And this again represents 1 ion of copper and 1 ion of this polyatomic group called sulfate. Okay, we're going to go ahead and look at our last 2. Our last 2 is between Li and N. Okay, we're going to look at this. We have 3 lithium atoms and 1 nitride ion. Okay, and so when we look at these, the reason that we got 3 lithium ions is because when we use the crossover rule, we cross these numbers over, 3 and 1, to get these. We cannot reduce that anymore. So this is how we are going to leave our ratios so that they balance out. So finally, as we go and do this, this is pretty simple in terms of how we carry that over. Since we have to represent these 3 lithium ions, we're going to make sure that our 3 is written over there. And since there's only 1 nitride ion, we don't have to write a subscript for that. And that's actually as detailed as we need to make that. Okay, and we see that our final thing is going to be very resemblant of this top one that we just saw. This Hg2+ is a mercury 1 ion. It's a cation with 2 mercury atoms in it that share some kind of bonding there. It shares a charge of +1 across 2 atoms. So it does act as a polyatomic ion, even though it has a strange formula, one that may not necessarily look like a polyatomic ion at first glance. This is also another polyatomic ion. The ratios are very similar because we can calculate them the same way we did lithium and nitride. Here is where you might get this wrong if you're not paying close attention. The first thing we need to do is carry over our formulas for each of the ions on their own. The second thing, though, we need to do is put a parenthesis around the Hg2. And the reason that I'm going to put the parenthesis around that is because I have 3 of them that I need to represent. And so what I'm going to do is represent that in this way. So I have something that looks a little confusing, Hg2 in parentheses, with another subscript of 3. And that means that I actually have 3 of these groups of mercury that are, each of the 3 of them are bonded together in their own way. There are 3 of them needed to balance out the charge on this PO4 3- ion. And so this is the one I think that gave most people a hard time. You're not going to be asked to do something like this very often, but what I want you to start to look at is to start to recognize some of the ionic species and know when it is that you need to use these formulas. Also, you need to know how to read this. This means that there are 3 of these groups and only 1 of these groups. Even though the parentheses, again, may not always be written around the polyatomic ion when there's only 1 of them, this is also a group of atoms that are bonded together. And again, with practice and just looking at this long enough, you're going to definitely be able to figure that out. We're just about finished for this. This is as far as we were able to get in class with going over the content and making sure that people felt comfortable with it. There's some more things that I want you to go over for homework. Number 4 and 5 on page 157. I want you to really try that out, naming these ionic species. And here it gives you a little bit of a hint as to what you need to start to look at. And down here it also tells you how to start to name these anions as well. Remember that some of the polyatomic ions that you'll see here, actually all of them that you'll see here, are going to be have special names and they're written out. For this one here, you can fill one in of your own choice. And also as homework, page 158. This one you're going to need to do a little bit of reading and thinking a little bit about. Some of this is review of how we use electronegativities. There are 2 practice problems here that you can go ahead and do. And you can use these 2 practice problems to look at the similarities and differences between these. So in this box here, compare and contrast these structures. In other words, to calculate the difference in electronegativities, or what is the difference in electronegativity from lithium oxide compared to disilver monoxide. Okay, figure that out. Figure out how the Lewis structures are drawn. How are they similar or different? Summarize that information in this box. If there is a similarity, if there is a difference. How are the formulas written? Are there any similarities or differences? Summarize that there. And then see what you can figure out with these here. And again, there are very similar atoms that are given to you in groups. There is going to be a difference though, and that's my hint to you as you start to look at these. So again, this is going to be due on 158. This episode of Chemistry Street was brought to you by the letters AL, CA, 2+, and by electronegativity. I'll see you all in class tomorrow.